This is section 6.8, and it's probably the most important section in the chapter. It's all kinds of applications that have to do with growth and decay models, Newton's law of cooling, something called the logistic growth and decay model, and that's what we're going to look at. And you are going to have something from here on your final exam, so you need to know that. It says at the top of your notes, find equations of populations that obey the law of uninhibited growth. In other words, the population just keeps increasing and increasing and increasing and increasing. There's not a lot of populations that do that because generally there's something that keeps it from going beyond a certain point, like they run out of food because there's so many people, etc., etc. So let's take a look at this. It says natural phenomena have been found that follow a law where an amount A varies with time t according to this function. The amount at some time, or the population number, is equal to, this is called A sub naught, which is the original amount, times E, there it popped up again, to the KT. And we call that the equation for uninhibited growth. A sub naught, I'm going to write this, is when t equals 0. So it's right when you start. And you can't have k be 0. Okay? It's a constant, but it's not 0. So let's take a look at what it looks like. There's a little graph there in your notes. And it says, if you start with this population amount, that equation would show you that as time marches on, it grows like this. So we would say A of t is equal to A sub naught e to the kt. And this would be your time, and this would be your A. And it just keeps growing and growing and growing forever with no boundary on it. In the same manner, you can have uninhibited decay. And that is when the k, right here in the equation, is less than 0. This one was when the k was greater than 0. Okay? So it's still a graph of the same equation. A of t equals A sub naught e to the kt, but k is less than 0, so it's a negative number. So let's say this is our initial population, A sub naught. What this says is that it continues to decline forever, or decay. And that's uninhibited decay. So this is uninhibited, I'm going to abbreviate, growth. And this is uninhibited decay. And we're going to look at some examples of real-world examples. So let's look at uninhibited growth of cells. It says a model that gives the number n of cells in a culture after a time t has passed is, all we're going to do is change the a to an n for a number, okay? So it's n of t, the number at any given time, is however many you started with times e to the kt, where k is greater than 0. All right? So let's look at an example. 1, where we have uninhibited growth of cells. It says a colony of bacteria that grows according to the law of uninhibited growth is modeled by the function n of t equals 100, so that's how many you started with, e to the 0.045, that's your k, times t, where n is measured in grams and t is measured in days. So this is a bacteria, so you're weighing them rather than actually counting them. All right? So part A says, determine the initial amount of bacteria. Well, we can read how many we have by looking at our equation, since that is what it means, but let's do it this way to prove it. That means we want the initial amount when we first started, so that would be n of 0. That would be where t equals 0. So I'm going to put zeros in for the t. It would be 100 e to the 0.045 times 0, which would be n of 0 equals 100 e to the, anything times 0 is 0, but anything to the 0 power is 1, so that's equal to 100 times 1, or just 100. That's how we know that that is our initial amount. And remember, that's given in grams. So that was easy. Let's look at B. It says, what is the growth rate of the bacteria? Well, when you have that equation, n of t equals 100 e to the 0.045 t, the rate is how fast it's growing. In other words, it's the K. And since K equals 0.045, as a percent, we would call that the growth, let me spell that out, the growth rate, and it would be 4.5%. Just move your decimal. So growth rate and K are the same, are two different ways to say the same thing. All right, let's look at C. What's the population after 5 days? So what we want is, what is n of 5? That's what we're looking for. So let's fill it in. 100e to the 0.045 times 5. Just put that in your calculator, and you're going to get 125.2 grams. That's how much it weighs. Remember, we're not counting the number of bacteria. That's impossible. We're just weighing. And finally, D, it says, how long will it take for the population to reach 140 grams? So this time, rather than n of some number, we're saying that amount needs to be 140. So we're going to finish the other side, e to the 0.045 t. We're trying to solve for t. So let's first get the e by itself, and then we can take the ln of it. So we're going to divide by 100. And we have 14 divided by 10, which is 1.4, equals e to the 0.045t. Once you get it looking like this, you can take the ln of both sides. Those cross cancel, so to speak. And you have ln of 1.4 equals 0.045t. I just wrote it now really as an exponential, from an exponential to a logarithmic. That's all we did when you do that. And now all we have to do to get t is divide by 0.045. So when you put it in your calculator, you're going to go ln of 1.4, enter, and then you're going to hit divided by 0.045. And you're going to get t is approximately 7.5 days. Because remember, the initial problem told us that time was measured in days. So these aren't hard at all because you can put it all in your calculator. It's just a matter of knowing how to simplify and get to what you want. All right, E, it says, what is the doubling time for the population? What does that mean? Well, if your initial, if n sub naught was 100, then the doubling time would mean that the population amount doubled. So it would have to be 200, wouldn't it? So we're going to do the same thing we did in D, but we're going to say, when will the population be 200? It's the exact same problem. 0.045t, divide both sides by 100, and you get 2 equals e to the 0.045t. Take the ln of both sides, those cross cancel. ln of 2 equals 0.045t. Divide by 0.045, just like you did in part D, and you get t is approximately 15.4 days. So when you start out with 100, it will double to 200 in 15.4 days. That's all that means. Number 2. This is another one. A colony of bacteria increases according to the law of uninhibited growth. If n is the number of cells and t is the time in hours, express n as a function of t. Well, we already know that. It's n of t equals n sub naught e to the kt. Now, we're going to do something a little different this time. In the last problem, we were given the k. We knew that k was equal to 0.045 because it was right there in the formula. This time we're not going to be given k. We're going to have to find it. So this was part A. Part B says, if the number of bacteria doubles in 3 hours, find the function that gives the number of cells in the culture. In other words, what's the k? How can we make this be a general equation for any time? So here's what we know. We know that n of 3 is the doubling equation, right? So n of 3 equals n sub naught e to the k times t, which is 3. I'm going to write that in the front. But we also know that this, at 3 hours, it's equal to twice what you started with. So I'm going to substitute this in for this. So I'm going to take that out and write 2 n sub naughts equal n sub naught e to the 3k. And this should look familiar because it's like when we were working with interest and we said the interest was going to double. Remember, I mean, not the interest, but the amount would double. So we're going to divide both sides by n sub naught. And you get 2 equals e to the 3k. We're trying to solve for k. Take the ln of both sides. That goes away. ln of 2 equals 3k. Divide by 3. And you get k equals ln of 2 divided by 3. Which, if you work that out, you'll get some answer, but I just want to leave it like this. We're going to leave it like this because this is exact and I don't want to approximate this. So the equation that we are looking for here is this one with the k taken out and this put in. So it's going to be n of t is equal to n sub naught e to the ln of 2 over 3. I know that's weird. Times t. It doesn't matter because it's going to be in a calculator, so it doesn't really matter what it looks like or how ugly it is. You don't have to do those longhand, which I'd like to see that. Okay, let's look at C. Using that equation, it says how long will it take for this size to triple, which means that n of t would be equal to 3 times the original amount. Well, since n of t is equal to n sub naught e to the ln of 3 over 3 times t, we're going to replace this with that. So triple the original would be this equation. Again, don't let yourself be bothered by how ugly it is. Divide both sides by n sub naught. And you get 3 equals e to the ln of 2 over 3t. Take the ln of both sides, and yes, I know I have 2 ln's there. It's okay. That goes away. And you have ln of 3 equals ln of 2 over 3 times t. Now, this is a little different because what we're going to have to do now, this is a fraction. And to get rid of a fraction, what you do is you multiply by its reciprocal, which is 3 over ln of t, correct? 3 cross cancels that cross cancels that. But if we do it on that side, we have to do it on this side also. And what we have is t is equal to 3 ln of 3 over ln of 2. And when you put that into the calculator, it's going to be approximately 4.755 hours. Okay, because if you go back to the original, it talks about t is in hours. So it's just a bunch of manipulations. Don't get flustered by this. D, how long will it take for the population to double a second time? In other words, increase to 4 times. Well, if you go back to A, it says it doubles in 3 hours. So without even working it out, we know that it quadruples, which is 4 times, right? Quadruples in 6 hours, because it doubles again. It's 2 doubles. Every 3 hours it doubles. So that's what we know. We don't have to work anything. Okay, now let's look at one about the law of decay. It says the amount of radioactive material present at time t is given by a of t equals a sub naught e to the kt, but this time k is less than 0, so this will be a negative amount. All right? Remember, that was our original equation, but in the one about the bacteria, we put an n just because we knew we were counting them. So let's look at example 3. It says, traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. If the half-life of carbon, I'll explain that in a minute, is 5,600 years, approximately when was the tree cut and burned? And then you notice it says, all radioactive substances have a specific half-life, which is the time required for half the substance to decay. That's what a half-life is. So, we're going to use this formula. A of t equals a sub naught e to the kt. Okay? First, we want to find k, because it didn't give it to us. But here's what we know. At 5,600 years, we know, or A of 5,600, we have half the amount that was original, half the original amount. So what I'm going to do is I am going to take the fact that A of t, or A of 5600, is equal to this, and I'm going to substitute it back into here. So what I would have is, instead of A of 5600, I would have 1/2 A sub naught equals, and then I'm going to do the other part of the equation, the right-hand side, A sub naught e to the kt. And you can see if I divide both sides by A sub naught, those are going to go away. And I have 1/2 equals e, to the kt. That wasn't supposed to be there, it's supposed to be up. Well, I can just take the ln of both sides, correct? I can take the ln of both sides, and I have ln of 1/2 equals kt, but we know what t is. T is 5600 in this instance, so it's times 5600. We know that. I could have replaced that right here. I just didn't think about it. I could have written that 5600 in for that t. So now, if I want to know what k is, I'm going to divide both sides of my equation by 5600. And what I get is k is equal to the ln of 1/2 over 5600. Another way to say that would be 1 over 5600 times ln of 1/2. I'm perfectly satisfied with this way, though. Alright, so it's going to be ugly, but when we write the equation, it's going to be, so A of t is equal to A sub naught e to the k that we found, ln of 1/2 over 5600 times t. And that is what the equation looks like. And aren't you glad that you have a calculator? So now let's go back to what it says. It says when they found it, this piece in the ancient tools, there was approximately 1.67 of the original amount of carbon-14. Well, 1.67% changed to a decimal is 0.0167. So instead of it being half of A like we did right here, we had 0.0167 of the original amount equals A sub naught, our formula that we got here. A sub naught e to the ln of 1/2 over 5600 times t. Divide both sides, those go away by A sub naught, and you have 0.0167 equals e to the ln of 1/2 over 5600 t. Now I'm going to take the ln of both sides to make that go away. ln of 0.0167 equals whatever's left here, ln of 1/2 over 5600 times t. To get rid of that, multiply it times its reciprocal, which is 5600 over ln of 1/2. So I have to do the same thing over here. 5600 over ln of, since this is a decimal, I'm going to write 1/2 as 0.5. And that's what, those cross cancel, t is equal to. So when you put this whole business in your calculator, what you're going to get is about, I should have written it this way, about 33,062 years. That's how old that was. That was when the tree was cut and burned that long ago. And you know what? That's used all the time in archaeology. That was a pretty complicated one, but it's still the basic processes are the same.